All right, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. I thank you for these students, this class, this opportunity we have just to meet together and study the mysteries of your creation, Lord, the math that you've allowed us to understand. I just pray you be with us today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so I lied. I'm actually not going to cover manifolds today because there is more algebra to settle, and we really do want to understand this algebra that we're doing today. So I'm going to try to do it somewhat carefully, as long as I can. So here's the context. We're going to study a vector space V over the reals with G, a mapping from V cross V to the reals, which is what? Symmetric, non-degenerate, a symmetric, non-degenerate, bilinear form. AKA a metric. Or if you read Rentlen, an inner product. All right. So what I want to describe then is how can we use this given metric to induce metrics? What is it? Oh, okay. I'm easily distracted. You know, you can tilt the screen to like look down so you can sit if you want, but if you don't, it's also fine. Okay, so what we want to do then is I want to describe to you how we can use this given metric to induce metrics on all of our other favorite spaces corresponding to V. What are those spaces? Other vector spaces, let's say, associated to V. Let's see, what would be in that, counted among that list? How about, yeah, V dual is one, right? But then a little bit more greedy than that, how about K forms, right? And then, of course, for K equals 1, 2, so forth and so on. And then, of course, you'd also like to maybe do just K vectors as well, right? So now, Rentlen uses the same symbol G for the induced metrics. I'm gonna say G tilde just so we have a distinction in terminology. So first of all, how can you induce a metric on this one? Right. Well, it has to do with non-degenerate, right? What's that mean? So, and we're gonna go ahead and do all these things with respect to an orthonormal basis. All right. So let's let E1, E2, En be G orthonormal. And then with dual basis, E1, E2, En as usual, right? What's the connection between these two? E upper I, E lower j, eating E lower j is Kronecker delta ij, right? Now G orthonormal, I can't say anything, does not mean that you might be tempted to think G orthonormal means that this is Kronecker delta ij, but that's not quite right. It's plus or minus Kronecker delta ij. That's what's meant by G orthonormal. Now let me be more specific, all right? We could introduce a symbol epsilon epsilon sub I, Kronecker delta ij, like that. And so the epsilon sub I is either plus or minus 1. All right. A typical convention is what? You might order the EIs with epsilon sub I equals to minus 1 at the start or at the end. So maybe it's like this, epsilon 1 equals minus 1, epsilon 2 equals minus 1, epsilon, what's the symbol for that? So I've been studying Lee's book because he got a little bit more detail than Rentlen on this point, and I wanted to try to expand on Rentlen a little bit because he's a little bit terse here on this point. So the index of G, all right, is the number of minuses here. Actually, I'll give a better definition for that in just a second here. Epsilon. I need a symbol for the index. I don't know what's a good letter. I need some kind of letter I'm not using for anything else. 7. Joe's not even here, and he's done it too.
If you did that, though, you could say you did it. And then he would be really upset and not have it.
All right. 7. See that? Oh man, I can't do it. I'm sorry, but this is called the signature, which is not S. What's that? P. Fine. P. I'll use P. P equals P equals minus 1, and then P plus 1. So that's a typical convention. Now, if you do that, then the matrix for G looks like what? Now, one of your homework problems is to show that if you have a symmetric, non-degenerate bilinear form, right, there in fact exists a basis, right, where you can get the matrix of the bilinear form looks like this, right? Now, the number of minus 1s is an invariant, like the number of minus 1s, the number of 1s is it's not. You don't have any flexibility over that. You're stuck with that. It's basically, and of course, more generally, there'd also be zeros, but this is non-degenerate. And so basically, if you start with an ugly bilinear form, it's your eigenvalues, if it's non-degenerate, they're non-zero, so they're either positive or negative. The number of positive eigenvalues is the number of 1s. The number of negative eigenvalues is the number of minus 1s when you go through the argument in your homework. Yeah.
So does it have to be equal to the number of negative 1s?
No, there's no, you could have any, so this is what we were calling P. Let me just, a little bit of background here before I get back to our main goal for today. So here's a better way of defining that would be this definition. The index of G on V is the dimension of W, all right, where W is a subspace of V, is the largest subspace on which G restricted to W is negative definite. obviously this definition is a better definition than the one I kind of sketched. Like my definition over here is based on, you start with an orthonormal basis, and if this happens, I mean, this is a nice definition because it captures what it is linear algebraically. There, you can also define in this world, right? You can also define W perp. What's W perp? I think I've said some of these things the other day, but I'm saying them again. Yeah, it's like V and V such that what? G of V comma W is equal to 0 for all W. In linear algebra, one of my favorite results that we get to is the theory that the perp is the orthogonal complement of W, in the sense that they're complementary subspace, they're direct sum, right? So G positive definite, right? If G is positive definite on the whole space, then usual linear algebra tells you that W direct sum W perp is equal to V again. No, what I'm saying is if G is positive definite on all of V, then and I'm not saying that this W is the same as the W up here. This is just, I mean, U here. I see what you guys are thinking. No, I didn't mean that to be the same W. Sorry, operator overloading. I mean, this is what we use this for our tangent and normal space discussion, right? Like if the normal space is 2-dimensional and you're in a 10-dimensional context, then the tangent space had to be 8-dimensional, right? Because whatever's not in the normal is in the tangent and vice versa. So the direct sum of the normal and the tangent spaces give you the total tangent space instead of all vectors at P. This is because you're using the Euclidean inner product, right? And it's positive definite. So there's something interesting that happens in the case that it's non-degenerate, but so here's the lemma. This is from Lee's book, but I think it helps bring a little bit more context and maybe texture to what we're doing today. Let's say, page 332 of Lee. Jeffrey Lee's. Manifolds and differential geometry book. Here's what it says. It says W, a subspace of V, is non-degenerate. What I mean by that is that the metric restricted to W, all right, is non-degenerate. Invertible is the wrong word. Non-degenerate. If and only if W direct sum with W perp is the vector space again. So I'm not going to prove that theorem, but what I will show you is an example of how it can go wrong. Because, you guys haven't seen many examples of metrics which aren't just inner products in the usual sense, right? Positive definite. So here's a good example. Let's look at V equals to R2 paired with G of, let's say, V comma W is equal to minus V1 W1 plus V2 W2. So in other words, this has got matrix minus one, sorry. It's got, so you could rewrite this as like v1, v2, minus 1, 1, 0, 0, w1, w2, right? So this is the matrix. The matrix of G is this, right? So consider W equal to the span of the vector 1, 1. So if we take the restriction, look at G restricted to W, acting on what? So a typical vector in there is just what? It's CC, right? What's that give you? Minus C1, oh, minus C times C, right? Plus C times C, which is otherwise known as 0. So in fact, the metric is identically 0 on this subspace, right? You see that? What's the perp? What's the perp of this subspace? Is it? That's what I was kind of expecting to start with. But you have to understand, this is not the perp with respect to the dot product. This is the perp with respect to this metric here, which has signature minus 1. So we have to look at, v1, v2, such that what? G of v1, v2, comma, and what's a typical? It's just CC, right? That's a typical W vector equals to 0. But this just gives you minus C v1 plus C v2 equals to 0, right? For all C, which implies that v1 is equal to v2. So in other words, this is something like v1 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 such that v1 is in the reals. In other words, it's W. Weird, huh? Yeah. So it's not even the case that W plus W perp is equal to V, right? W plus W perp is just equal to W again, which is not equal to V, right? So it's certainly not the case that we have the direct sum decomposition. So you got to be careful when you're working with metrics which are not positive definite.
So that means it's non-degenerate.
Right. If it's non-degenerate, if you're going to do something with a subspace and you want to use the orthogonal complement idea, you got to be careful that the metric is non-degenerate with respect to that subspace. Otherwise, you lose things like this. Now, the physical meaning of this, what I just did to you guys, was the light cone here. If you think of this as space-time, t and x, so these vectors along the 45 degree in the Euclidean sense, the so-called light cone. Light cones have metric 0. I mean, you see that the inner product of the null vector with itself is 0 again. And so what I did was I took a subspace which fell on the light cone. And that's going to be generically a problem for the linear algebra in Minkowski space. Minkowski space, more generally, guys, you can build off this example. You can look at Rn with the matrix with metric minus 1 and then 1s. This is what I called before Minkowski n space, right? And so in there, if you just take anything like the span of the first vector plus one of the other ones, then it'll fall on the light cone, which is a hypercone. It's a higher dimensional cone. But any subspace, any linear subspace which falls on the cone, it's going to have this problem. I just wanted to warn you. I know things sound a lot alike, but there are some pitfalls here that we have to be careful for. Anyway, so that said, let's come back to our problem now that we have a little bit better sense of what's going on here. In order to understand what the metric we want on these is, we need another thing. We need to also talk about the inverse to the metric, right? So I'm going to just... So we have that non-degenerate. What's non-degenerate mean? That means that g of x, y is equal to 0 for all y in v implies that x is equal to 0. So what that means is if you look at this, right? If you look at this, what's that?
That sounds a lot like the definition of
Yeah. For fixed x, you're right. I mean, if I look at the mapping L of y, right, is equal to g of x comma y, then this condition above is exactly the statement that, you know, this is injective. Well, to be more precise, has the kernel of L equal to 0 if and only if G is non-degenerate. But it's not quite that, because this also has to happen. X is arbitrary too, right? So maybe I should put it L sub x or something. Is that what you're saying?
I mean, wouldn't it be L of x?
Oh, I'm sorry. Oh, yeah, you're right. I'm exactly I just got turned around. Yes, you're right. So I should say L of maybe L sub y of x is equal to 0. Has kernel of Ly equal to 0 for each y in V. That would be equivalent to the non-degeneracy, yeah. But the point, though, is if we look at this as a matrix equation, right? If I look at this, let's see. So we define. See here, we can look at g of, let's say, g of x sum over I, xi ei sum over j, right? Yj ej. That's equal to a sum over I and j of x upper I, y upper j. And then we have, well, what I would usually denote as g lower ij, where I just defined g lower ij as in the usual way. It's g of ei comma ej, right? G is a symmetric bilinear form. It's a tensor. Those are its components with respect to the given basis. Now we have that this is equal to 0 for all y, right? So in particular, you can rewrite this as, something like g I j, let's say xi sum I equals 1 to n is equal to 0, right? I can take the case that I can look at the y that's just ej, and that gives me that equation. And that's true for, and that implies x is equal to 0, right? In other words, this gives you the matrix gij times the vector x is equal to 0 implies that x is equal to 0. And of course, basic linear algebra tells you that you can do the converse, right? So that means that this matrix is invertible. So if it only has the 0 solution, therefore Gij is invertible. Do we agree? So a little bit of notation then. We define the inverse to be G upper Ij is equal to the matrix inverse of this one. So what does that mean? That means that if I have the sum, let's say over J equals 1 to n, of G upper I, J, G lower JK, I get the Kronecker delta IK. It's an inverse. So this is what, this is what Gij inverse times Gij equals to the identity matrix looks like when you look at it in components. The ikth component of this matrix identity gives us this tensor formula. And vice versa, right? I can also multiply them in the opposite way, right? I can go sum j equals 1 to n of Gij, G upper jk gives me Kronecker delta ik. So we have these fundamental intertwining relations between the metric and its inverse. It's the inverse of the metric. It's the inverse of the matrix of the metric. People call it the inverse metric. Of course, technically speaking, it's not an inverse function, right? Because the metric is a mapping from v cross v to r, and you can't find an inverse from v cross v to r because they're quite different spaces. There's no bijection between the Cartesian product of an n-dimensional vector space and itself in the reals. Okay, so there's really not much danger of confusion there by calling it the inverse metric. So I will also call it the inverse metric. Are we good? All right, so what's a metric on V-dual? Well, but first let me ask a different. Let me do something slightly different. Let me suggest an isomorphism. It's supposed to be an inverse where? Oh, I'm sorry. Yes, I should say. Very good. Right, because I have it, right there. G upper ij is the inverse of G lower ij. Yeah. Again, as I warned, the one place where we can't make the conventions, the index upper lower conventions, quite gel is when we make definitions. Like, definitions almost always violate the index convention somehow. I mean, you see that a lot, but it's just a convention. So I would think of the up-down indices as a mnemonic for remembering certain isomorphisms. So what's an isomorphism of the vector space in its dual? I'm going to propose to you that the following we can do. So let's let x be an element of V. All right. Then if we look at G of blank, comma, well, I forget if it doesn't really matter because G is symmetric, right? I could write this, or I could write this. It doesn't really matter because G is symmetric, right? Then that is a dual vector, which naturally corresponds to x. Let me be more precise here. So the flat of x is equal to G of, let's say, x comma blank. Or sometimes people write a dot. So here, the flat is a mapping from V to V dual. I've taken a vector and I've made it into a form. Now, how do the components of B flat, flat, the flat of x and x compare, right? Let's figure that out. So if x is equal to a sum over I of x upper I, e lower I, then if I say alpha is equal to x flat, I'm working on drawing my flats, I'm still not quite. If alpha is the flat of x, then what? Then let's see here, alpha of e lower I is equal to g of what? X comma ei. So Jess, what we're doing is we're defining an isomorphism between V and the V dual using the metric. What we're going to do is we're going to take x, put it in one of the spots of the metric, leave the other one free to vary. That gives us a linear function, real valued linear function from the vector space, to the reals again. And so that makes this a dual vector. And that has this isomorphism has a special name, it's flat. And I'll explain the meaning for the yeah, like the flat in music. This is one of the musical morphisms. It's one of the musical morphisms.
Is it really what it's called?
Indeed. It's a musical morphism. There is a sharp. We'll get there. Okay, so this would be a sum, sum over, let's say, j equals 1 to n of x upper j, right? And then I've got g of ej ei. So then, let me just clean that up a bit. So we could say alpha sub I is equal to what? Alpha sub I is equal to, continuing the discussion, alpha sub I is equal to a sum over j of x upper j, g lower j I. Now, in physics, what they'll do is rather than using they'll just basically use the same letter for the isomorphic copy of x. And so in that notation, this becomes x lower I is equal to x upper j gj I. And this is called lowering the index I, lowering the j index. Technically, what's going on, though, is you're changing the type of object you're looking at. You're changing the vector to a dual vector by exploiting this musical morphism. So if you wanted to undo a flat, what would you do? Yeah, so sharp of flat of x is just equal to x again. And the sharp, the flat of the sharp of alpha should be equal to alpha again. Let's see here. So if you, in other words, we're saying the sharp of this alpha that this alpha right here, right?
What is alpha then?
Should be x again. Here, this is for alpha in the dual.
So alpha's in the dual and x is in the
Yeah. Now, so this is definition That's a definition of the sharp. The flat I already defined. But let's see here. So continuing with this particular alpha, if sharp of alpha is equal to x, what was alpha? We have a formula, right? It's sum over j, 1 to n. Well, I'm sorry. The sums are always from 1 to n for now. X upper j, gji, right? There is something else here, isn't there? Oh, that's alpha vi. What do I need to do to make it alpha? Right, this. Gosh, good grief. All right, sharp of the sum over I of alpha I e upper I is equal to x again, right? So we're going to define that to be linear, right? So good grief, sum over I of alpha I, the sharp of e upper I should be equal to x again. I'm sorry, this is clear as mud what I'm doing. Fine. You know what? I think I can continue down this path, and after another few minutes, we'll get to what I want. I tell you, now I've done this much. Let me just stick with it. So this gives us what? Alpha I was the sum over j, and then of course the sum over I is still there, right? But alpha sub I is x upper j, g lower ji. And then I've got the sharp of ei, whatever that is, right? That's all equal to x, which is equal to what? Sum over, let's say, I'll say k of xk ek. So if these are going to be equal, fine. This is awful. What have I done? What have I done? The kth component of that, right? What I'm trying to argue is that, and I think I'm doing it in probably about the most inefficient way possibly you could do it, is that this and that have to be the same, right? Okay, so finally, I have that x upper k is equal to a sum over I and j of x upper j, g lower j I, e, the sharp, whatever it is, we're trying to figure that out, sharp of ei, the kth component of that. Well, I'm tired of this. Are you tired of it? I'm tired of it. Definition. The sharp of alpha is equal to, well, let's be more clear. The sharp of alpha, the ith component of that, all right, is going to be the sum over j of, and so what we start with is if for alpha covector, right? So, and I'm assuming alpha is equal to a sum what? Sum over I of alpha sub I e upper I, right? So what we do is we do g, or maybe I should do j here. It'll be easier to see what's going on. Sum over j of gi j alpha sub j. Or you might write this, the sharp of alpha sub I is just equal to g ij of alpha I. If you're using the, alpha j, if you're going to use the repeated index convention that when they're repeated, they're summed over. But in fact, in physics, they wouldn't even write that. They would just write, they don't even write the sharp. They just say this. Let me put some protective green bubbles around the physics notation. Partition it from the world of summations and such. All right, so yeah, that's what we would get to eventually. As I study this, I would eventually find that the inverse, I needed the inverse metric to solve for this. Now, I can just claim that that's the inverse and we can check. That's pretty easy, right? So if I take the sharp of the flat of, alpha, of x, right? What should that be? That's the sharp of the sum over j of xj gji, right? Oh, I keep forgetting. I have to do what? I have to add the basis element too, right? So so there's an EI here as well, right? The flat takes a vector and turns it into a dual vector. So, and then what do you do? This is, so basically this whole thing, I say the sum over ijk of what? Oh, why am I doing k? Oh, so g k I x j g j I e k. And the point is that these two produce, as we contract over the I, these produce a Kronecker delta kj, right? And so we're left with sum over, say, whatever you want, sum over j, let's say, of xj ej, which is otherwise known as x. Are we good? All right. So we have these musical morphisms. And, I mean, you can see that this is a linear. You can easily prove that this is an isomorphism. Maybe I'll try to have a homework problem where I state these carefully and just ask you to prove that they're isomorphisms. It's not a hard problem. And it'd probably be good to settle whatever confusion lingers from my failed attempt at this. Sorry. It's not failed, it's just incomplete, I should say. Now, now that we have these musical morphisms, we can convert vectors and covectors, vice versa, right? But you can do so much more than that. Let's see here. So I said we wanted to induce metrics on other things, right? So what would be the metric, let's say G tilde, on V dual, cross V dual to the reals? How would you define it? Now the typical, so G tilde, let's say alpha, alpha beta. What would you do? We already know G yeah. That will be bilinear because it's a composition of linear objects and bilinear objects. Linearity of the sharp, bilinearity of G transfers to bilinearity of G tilde. Neat? No? Okay. All right. But we don't stop there. What I really want is a metric on the exterior algebra. So let's look at the next thing. Let's try to figure out, let's see here. Well, there's a couple different ways to go at this. I'm gonna first of all, I'm gonna show you, I'm gonna go back to my roots, show you the physics way of doing it, physicsy way. So if I have a form, alpha, and it's a K form, I can express it in the sum over all multi-indices like this. It's alpha I1 ik, and this is just I1 ik, no restriction. I have to put a 1 over k factorial if I do that, because I'm not really working with a basis over here. Let me check on that just a second. Make sure I'm not violating my conventions. Sorry, I wrote too much. It's hard for me to find what I want. Where'd it go? I'm mainly wondering if, I'm trying to make sure that I'm supposed to have a wedge product there and not a tensor product. That's what I'm worrying about, if you guys are wondering. Pretty sure I want it to be wedge. Yeah. Now, for what it's worth, you could also write this as a sum over, let's say, alpha I EI, where this was, EI was EI1 tensor EI2 tensor tensor EIK. And we could use, and I'm introducing a new notation, guys, here, whereas this I would denote EI vector. If we want to have our cake and eat it too, we can use unvectored multi-indices to indicate just tensor, whereas with a vector, it indicates wedges like that. And so this sum over I, that would just be all possible multi-indices. So I could do like 1, 2, 3. I can do 2, 1, 3. I mean, I don't insist on increasing. This I could. I mean, you could also write this. You could also write this as a sum over I increasing of alpha I increasing indices E I increasing. Now, of course, this is only true for alpha in the k-forms. Right? And actually, what I'm just writing here is very much not physicsy. Sorry, to be honest. But anyway, if I want to define, I can do something like this, right? I can say alpha j1, j2, dot 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 jk is equal to what? How do I raise indices on a form? I do jj1, I1, j2, I2, dot 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 gjk, ik. Oops, I forgot my sum. I mean, I'm not being physicsy enough here. Of course, I have to sum over the i's. And then I would have alpha, I1, I2, da da da, alpha k, oh, ik. You raise the indices like that. And then, by the way, well, sorry. If I wanted to then define what's the inner product between two such things, and I'm still using g tilde, maybe I should say g tilde k or something here, I don't know. But for alpha and beta being two such k forms, the definition then would just be it's the sum over, and now I got to worry about a normalization. It'd be the sum over, sum over I, all possible, 1 over k factorial. So this is all multi-indices, not necessarily increasing multi-indices, sum over I of alpha, upper I, beta, lower I, like that. Now, this is the same if you work with increasing multi-indices as this. Like that. So this here is what? But that is this. All right. And what is that? Well, these two go together to give us a Kronecker delta IL, right? So you're left with I'll keep the I, J, K, I have G, I, K, alpha K. I said Kronecker delta IL, I'm keeping the I, so the L becomes an I. But you see what this is? That's exactly alpha upper I, right? So what you have then, and I think that the J got used up already. I already used that in the last step, sorry. So that gives us a sum over alpha I, beta lower I. So that's actually what we just did over here. But here you'd be using not just one musical morphism, you use k-fold musical morphisms, one in each entry. And in fact, that will define a metric on the set of k-forms. There's a more careful and beautiful construction of this which is sketched in Rentlin, which I'll try to make into a homework problem. Your next homework is also just going to be algebra. We'll have 2 homework sets which are really just multilinear algebra forms. I think it's healthy. The thing I was talking about last time, whether or not you can write a vector in terms of wedge product of a given set of vectors or something, that goes into what's called decomposable. That thing I was talking about last time was decomposable. I'll try to figure out some homework problems on that which are interesting, but there's a lot more I had to say today, which I'll try to reformulate into homework problems that are manageable. Okay, so that is a metric, though. You can prove that this is symmetric. That's kind of obvious that this is symmetric. It's definitely bilinear in alpha and beta, right? And the non-degeneracy stems from the it's a composition of invertible things with a non-degenerate metric. So it's still non-degenerate. So then you extend this. How would you define the inner product on, say, on this? So this is R, direct sum with V dual, right? Direct sum with the 2 forms, direct sum direct sum with the n forms over V dual. How would we get a metric on that? Well, we're going to talk. Let me talk about degree for a second here. This is degree 0. This has degree 1. This has degree 2. This has degree n. So let's say degree is the number of dual vectors that appear in the, if it's a homogeneous element, it has definite degree. The degree is just the number of dual vectors it takes to wedge together to make the object. So like 2 vectors, a 2 form has degree 2, an n form has degree n, right? This thing I'm describing to you right now is actually why the exterior algebra is a graded algebra, right? There's some kind of natural bijection between the algebra and, well, in this case, the numbers 1 through n, or 0 through n, rather. Okay, so how would you define, for example, then, if you want to extend this metric, how would you say, like, suppose you had, E1, comma, E1 wedge E2, what would you say the metric on that would be if we're trying to think of how to extend G tilde to the whole exterior algebra? Or what would G tilde be on E1 wedge E2 wedge wedge En and E1 wedge E2, whatever. I mean, these kinds of things where we're taking the metric of terms of inequivalent degree. What should it be? I mean, we're making a definition. You can make it whatever you want, but we're going to make it to be 0. I mean, you can't make it whatever you want. You have to make it some way that's consistent with making something a metric, right? But if you make those 0, right, then you can just piece together the ones we've done at each order of k, and you'll get a big metric for the whole thing. So in this way, we define a metric on the entire exterior algebra, basically building into this metric the idea that forms of distinct degree are orthogonal. So we have this G tilde, right? Which is a mapping from the entire exterior algebra across the entire exterior algebra of V dual, right, to the reals. The question is, what can you do with such